AI peer review. Okay, welcome back. So large language models, they're incredible on their own, right? Cornerstone of so much progress.
Absolutely. Transformative tech.
But we've all seen that where things get really interesting often is when you start orchestrating them, putting them together into multi-agent systems.
Hmm.
You get collaboration, complex problem solving, things a single agent might, really struggle with. We're seeing that capability just blossoming.
Yeah, the potential is definitely huge. But as anyone who's actually tried to build one of these systems knows, moving from a cool demo, maybe two agents chatting, to something robust, reliable, a
Oh,
workflow that consistently works on a tough task.
that's hard.
It is. It feels less like engineering with clear blueprints and more like, well, like trying to fine-tune some kind of Rube Goldberg machine
Uh, yeah,
made from these incredibly powerful, yet, let's be honest, somewhat unpredictable parts. You feel like you're balancing just countless knobs and levers kind of in the dark.
that analogy definitely hits home. You're asking, okay, how many agents? What's each one's job?
Exactly.
How do I prompt them so they actually do that job consistently?
Right.
And then how do they even connect? Is it a chain, parallel? Do they debate? Do they refine each other's work?
Right.
It's a really daunting design challenge.
It really is. And that specific challenge, that complexity, is exactly what's tackled in an interesting paper we're looking at today.
Okay.
They take a pretty rigorous approach, proposing a framework to try and bring some much-needed automation, some principled design to creating these effective multi-agent systems.
Automating multi-agent system design. Wow. Okay, that sounds like a total game changer for anyone wrestling with these build problems.
Potentially, yeah.
So our mission for this deep dive, let's unpack the complexities. What makes multi-agent design so hard, according to this paper? Then understand their framework mass, you said. MASS.
That's right. Multi-agent system search.
Okay, how mass tackles these challenges head on, and importantly, what insights did they uncover? What really matters when building these things?
Yeah, the core problem they identify and what they're really trying to solve is this recognition that an effective system isn't just, throwing together a bunch of powerful individual agents.
Right. More isn't always better.
It's fundamentally about how you program those agents, their prompts,
Yeah.
for their specific roles, and crucially, how they connect and interact, their topology.
Prompts and topology.
Exactly. The
Yeah.
paper argues this combined design space prompts and topology. It's just vast. It's incredibly complex.
Mm.
And a lot of prior work. It tended to focus on optimizing just one of those aspects, kind of in isolation.
Okay.
So they aim to analyze and find a way to efficiently search this combined space.
Got it. So if you've been exploring multi-agent systems yourself, maybe building workflows with LLMs, or just trying to figure out how to make your AI apps more robust, more capable than what a single prompt gets you, this deep dive is definitely for you. We're going to get into the technical weeds where it matters, really understand the difficulties and this, well, potentially very clever new approach to solving them. Okay, let's start where the paper does. Before jumping to the solution, they really dig into the root causes. Why is designing effective multi-agent systems so inherently difficult right now? What are the core challenges they're laying out?
Yeah, they highlight two main culprits, and these really compound each other, making that design space just so tricky to navigate.
Okay.
The first one stems directly from the building blocks themselves, the LLMs. As the paper notes, and they reference some prior work here, individual agents powered by these models suffer from something we hear a lot about, prompt sensitivity.
Prompt sensitivity. Yeah, it's a familiar term, but maybe worth unpacking quickly. What does it mean in practice when you're trying to build these systems?
Well, it means that even seemingly tiny changes in how you word a prompt.
Like changing a few words.
Exactly. Maybe just rephrasing a sentence slightly, or changing the order of instructions, even adding a phrase you thought was clarifying. It can lead to really significant, often totally unpredictable drops in performance.
Right.
You might have a prompt that works great, you tweak one little thing, and suddenly the agent just misunderstands
Right.
or fails at its core task. It's brittle.
Yeah, feels like walking on eggshells sometimes with the prompts. You find something that works and you're almost afraid to touch it.
Precisely.
Yeah.
Now take that brittleness and imagine cascading it. That's where the problem gets much, much worse in a multi-agent system.
Because the output of one feeds into the next.
Exactly. You're often taking the output from one of these sensitive agents and feeding it as input to another sensitive agent whose output might go to a third, and so on.
Okay.
So this cascading effect means that prompt sensitivity can get, well, severely amplified. A small error, A slight misinterpretation early in the chain because of a subtly off prompt. It can propagate. It can completely derail the entire workflow downstream.
Leading to just completely wrong results.
Or irrelevant results, yeah. Total failure. So that's challenge number one. Sensitive components amplify errors.
Okay, what's the second major challenge?
The second one, which compounds the first, is designing the topology, the structure.
How they connect and interact.
Yes.
Yes.
How do these agents actually connect? How do they interact? Is it a simple sequence like A passes to B, passes to C?
Oh, parallel.
Or parallel, yeah?
Yeah.
Multiple agents tackling different parts of a problem simultaneously. Do they come back together to debate? Or maybe refine each other's answers?
Self-reflection, maybe. Summarizing steps.
All of those are possibilities. Reflection loops, summarization stages, tool use integration. It's all part of the topology design.
And designing that structure isn't like traditional software architecture, is it? Where you have clear interfaces, expected behaviors.
Not really, no. Because the agents themselves are so flexible and crucially so sensitive to their prompts, designing their interaction structure often involves just a huge amount of manual experimentation.
Trial and error, basically.
A lot of trial and error. You try a simple chain. You tense it. Maybe it fails. Okay, let's try adding a reflection step after each agent. Test that. Does it help? Does it actually hurt performance? Maybe we need a debate phase. Let's try that. Test it.
Right.
And when you combine this, well, frankly, enormous combinatorial space of possible topologies, different agents, different ways to connect them, different interaction patterns, with the completely unbounded space of prompt variations you need to make each agent effective within that specific structure.
You just end up with this astronomical number of possibilities.
Exactly. A massive high-dimensional search space.
Yeah.
And it's practically impossible for a human designer to explore that systematically just through manual iteration.
Makes sense.
Now, the paper acknowledges, prior work has made great strides automating parts of this.
Right, like DSPy for prompt optimization.
Yeah, systems like DSPy are great at finding good prompts and few-shot examples, but usually for a given fixed workflow structure. And then you have other systems like 8S and AFlow that have explored automating the topology search, trying to find good structures automatically.
But they often don't focus as much on the prompts within those structures.
That's the gap the paper identifies. They argue there's been this critical missing piece, explicitly addressing the interplay, the connection between optimizing the prompts and optimizing the topology at the same time.
Gotcha. So optimizing both together.
That's the goal.
Yeah.
And that's the gap Mass is designed to fill. Okay, so before they actually propose their framework, Mass, they do something really crucial, which I think is a great methodology.
What's that?
They step back and conduct a systematic analysis of this complex design space. They want to understand, okay, what factors actually have the most influence on performance?
Right, where's the leverage?
Exactly. Is it the prompts? Is it just scaling up the number of agents? Is it the specific type of topology? They looked at all of these.
Smart. You need to know what knobs actually do something significant before you start turning them randomly. So what did they find? Was it prompts, topologies? What mattered most?
Their analysis produced a really significant insight, and it really shapes their whole approach. They found that prompts frequently form a highly influential design component.
Okay.
What they demonstrate is that if you start with strong, well-prompted individual agents, you can often get surprisingly strong performance from the system right from the get-go, sometimes even before you add complex structures.
Interesting. So the foundation matters a lot.
Hugely, and they show this quantitatively. Figure 2 in the paper is really illustrative here.
Okay, figure 2. What's it showing?
It's comparing accuracy on the math benchmark using Gemini 1.5 Pro. They compare a strategy where they first optimize the agent's prompt and then apply self-consistency. They label this prompt SC.
Self-consistency being like generate multiple answers and pick the most common one.
Exactly, a simple form of aggregation. So they compare that prompt-optimized approach against just scaling up agents using standard non-optimized prompts, but employing common techniques like standard self-consistency, SC, self-refine, reflect, or multi-agent debate.
Okay, I'm looking at figure 2 now. The difference is, yeah, it's pretty stark, especially looking across the token count axis.
It really is. Notice the line for prompt SC, the prompt-optimized one. It starts higher and climbs much more steeply, right?
Yeah, definitely.
It achieves significantly higher accuracy for the same, or sometimes even fewer, total tokens compared to the other methods that just scale the topology with standard prompts.
So better bang for your buck, computationally speaking.
Precisely. It demonstrates this token effectiveness advantage you get from nailing the prompt early on. More accuracy, less compute costs because the basic instructions are just better. Even just adding simple self-consistency on top of that already optimized agent shows much better scaling. It saturates higher than standard SC or Reflect, which plateau earlier even though they use more tokens overall.
Okay, so takeaway number one seems clear. Fixing the prompt for the individual agent, that's potentially the biggest single boost you can get right out of the gate. Low-hanging, high-impact fruit.
Absolutely. It provides that strong foundation. And this finding really suggested to them, okay, optimizing agents locally, first getting that individual block prompt right, is not only effective, but also computationally more manageable than trying to optimize prompts inside a huge complex system from scratch.
Right.
And that insight directly drives the stage structure of their mass framework.
Okay, so prompts are key. What about the topologies? The structures, they analyze those too, right?
They did. Figure 3 focuses on that. It shows the performance of various common topologies, SC, Reflect, Debate, plus some task-specific ones like Summarize and Executor relative to a baseline single agent. And importantly for this analysis, the agents within each topology had already undergone their own prompt optimization.
Ah, right, so this isolates the impact of the structure itself, assuming the individual components are already pretty good. Did adding structure generally help them?
This is where the second, equally important, and maybe more surprising finding comes in.
Oh.
Not all topologies are beneficial, even with optimized agents.
Really?
Yeah, this is critical. The paper found that influential topologies, the ones that actually provide a performance gain over a strong optimized single-agent baseline, represent only a small fraction of all the possible ways you could connect agents.
Wow, so most complex structures might not even help.
What could even hurt?
Mm-hmm.
They show this with concrete examples. On the Hotpot QA task, only the debate topology gave a noticeable gain, about 3%, over the optimized single agent.
Okay.
Other common ones like SC, Reflect, Summarize, they either didn't improve things or, like Summarize on Hotbot QA, actually degraded performance by 2% compared to just the single agent baseline.
That's pretty counterintuitive.
It is. And they saw similar trends on other tasks, like Live Code Bench.
You'd think adding more thinking steps like reflection or debate would almost always be better.
You might assume that, but the data here suggests otherwise. It tells us that simply adding more agents or layering on more steps like reflection or summarizing isn't a guaranteed path to improvement, even if the agents themselves are well prompted individually.
So what does it depend on then?
It seems to depend heavily on the specific type of interaction you introduce, whether that structure is genuinely suited to the demands of the task, and how well the agents are prompted for that specific collaborative role.
Ah, okay. So you need the right type of interaction, and the agents need prompts optimized for that interaction, not just optimized in general.
Exactly. It's a combination.
Okay, so summing up the analysis. First, optimize individual prompts. That's high leverage. Second, be really selective about topologies, because most might not help, or could even hurt. Find the influential few.
Precisely. Those two core insights, the fundamental importance of prompts and the sparsity of truly beneficial topologies, they become the pillars for the mass framework they propose. They realized they couldn't just search blindly. They needed an informed, structured approach.
All right, the analysis gives them the lay of the land. Prompts are critical. Good topologies are rare. How does MASS, the multi-agent system search framework, actually automate finding the best combination? How does it avoid getting lost in that massive search space?
So MASS is specifically designed around these insights. It tackles the problem by interleaving optimization stages.
Okay.
The core idea, the intuition, is to go from local to global. You start by optimizing at the block level, the individual agent prompts, and then move towards optimizing the workflow level, the overall topology and system-wide prompts.
Local to global. Makes sense.
Yeah. If you look at Figure 1 in the paper, that gives a nice conceptual overview. And Figure 4 shows the components and the data flow more concretely. The framework works by combining prompts with these predefined agentic building blocks, things like aggregate, reflect, debate, summarize, tool use, standard interaction patterns.
Got it. And how does it structure the optimization? You mentioned stages.
Exactly. It unfolds over 3 distinct stages. Algorithm 1 in the paper lays it out clearly. Let's walk through them.
Okay, stage 1.
Stage 1, block-level prompt optimization. This directly tackles that first big insight, the importance of the initial prompt. So before they even try connecting agents in some complex way, the very first thing they do is make sure each individual agent or each minimum functional building block is as effective as possible, either in isolation or in its most basic setup.
How do they optimize those prompts? Manually.
No, crucially, they use an automatic prompt optimizer.
They specifically mention using MIPRO, that's Model-Based Iterative Prompt Refinement Optimization, but the general idea is Automatic Prompt Optimization, or APO.
So another system, maybe an LLM, is doing the prompt tuning automatically.
That's the idea. APO systems often use an LLM or some algorithm to iteratively generate prompts, test them, see how well they perform on some metric, and then refine them based on that performance. So in stage 1, MAS uses this automated process to optimize both the instructions and maybe the few-shot examples for each fundamental agent type or minimum block, like a single predictor or a basic two-agent debate block.
Getting each Lego brick perfect before building the castle.
Good analogy, yeah. And as Figure 2 suggested, optimizing the single agent, or these minimal blocks, is much more computationally manageable than trying to optimize prompts for a whole complex system at once.
Right.
It gives you that strong, well-performing foundation. They mention they start by warming up an initial predictor agent using APO. Then they optimize other block types like that minimum debate block, maybe 2 predictors feeding 1 debater, and they optimize that block conditioned on the already warmed up predictor's capabilities.
Sort of layering the optimization.
Exactly. It helps manage the complexity. Table 3 in the paper actually shows the specs for these minimum building blocks for the different topology types they consider.
Okay.
Now, also as part of stage 1, they calculate something really important for the next stage. The incremental influence score for each block. They call it an II.
Incremental influence.
Yeah, it's basically a measure of how much performance gain each optimized block gives you relative to the performance of just the initial basic single agent.
So it quantifies how powerful that type of interaction block is once optimized.
Precisely. How much potential value does adding this kind of block like debate or reflect bring to the table? And this influence score becomes absolutely crucial for stage 2.
Okay, makes sense. So stage 1, optimize the pieces, measure their power. What's stage 2?
Stage 2, workflow topology optimization.
Yeah.
Okay, now you have this library of individually optimized agent blocks from stage 1, each with its own influence score. The focus shifts to the overall structure. How should we connect these optimized blocks?
Right, the topology.
And remembering that second key insight from Figure 3 beneficial topologies are sparse, they're rare. They use those influence scores from stage 1 to intelligently prune the search space.
Ah, so they don't just try every random combination.
Exactly. They're not searching blindly. It's an informed search.
How does that pruning actually work? How do the influence scores guide the search?
They do something quite clever. They convert the influence scores into selection probabilities using a softmax function. So a block type that showed high influence in stage 1 gets a higher probability of being selected or activated in a candidate workflow. Then, when they're generating potential workflow structures during the search, they use rejection sampling. This is sample potential structures. But if a sample structure includes a topology dimension, like adding a debate step, that had a really low influence score in stage 1, well, if a random number U is greater than its low selection probability PA, that candidate workflow featuring the low influence step is less likely to be explored or might just be rejected outright.
So it biases the search towards structures built from high-influence components.
Exactly. It naturally favors compositions of agent types that showed promise individually in stage 1. It guides the search towards more promising regions of that huge topology space, while still allowing some chance to explore less obviously beneficial structures.
Smart. Does it constrain the structures in other ways, too?
Yes, to keep things manageable, even with the pruning, they also constrain the workflow structures they consider. They use a rule-based order for composing topologies, like a predefined sequence. Maybe summarize first, then reflect, then debate, then aggregate. Within this pruned and constrained space, they use rejection sampling to generate candidate workflow configurations, WCE. They evaluate these candidates on a validation dataset, keeping the ones that perform best and rejecting ones that are invalid or maybe exceed some computational budget.
Gotcha. And Table 2, you mentioned, shows the specific search space for each task.
Yeah, Table 2 details which topology types were allowed for each benchmark. And Figure 8 has some nice visualizations. It shows some of those minimum blocks from Stage 1 and examples of the best topologies that Stage 2 actually discovered for different tasks.
Okay, so Stage 1 optimizes the pieces and tells you which pieces are powerful. Stage 2 uses that power rating to intelligently search for the best way to assemble those pieces. That makes a lot of sense, leveraging the easier Stage 1 work to make the harder Stage 2 search tractable.
Precisely. It's informed search, not blind search. Much more efficient than trying to optimize everything from scratch simultaneously.
Okay, we've got optimized blocks, Stage 1, assembled into the best structure, Stage 2. Is that it, or is there a Stage 3?
There is a Stage 3. Stage 3, workflow-level prompt optimization.
Ah, more prompt optimization.
Yes. So once Stage 2 finds the best performing topology, let's call it WVNG,
Yeah.
based on the validation results, they don't just stop. They take this entire integrated system, that specific arrangement of optimized blocks found in Stage 2,
Yeah.
and treat it as one single entity.
Okay.
And then they run another round of prompt optimization using APO again, but this time on the entire workflow. So the output is W, which is the result of optimizing WC.
Okay. Why optimize prompts again? Didn't stage 1 already make the prompts for the blocks as good as possible?
That's a really crucial point, and it gets at the subtlety of how agents interact. Stage 1 optimized prompts for blocks in isolation, or in their minimal context. Those prompts made the individual pieces strong, yes. But when you connect those pieces into a specific complex system, maybe the output format of Agent A needs to perfectly match what Agent B expects as input in this particular workflow. Or maybe the agents in a debate need to coordinate their timing or style in a very specific way for this task. Prompts optimized in isolation might not be perfectly synergistic for those system-level interactions.
Okay. So stage 3 fine-tunes the prompts for the team, not just the individual players.
Exactly. It's an adaptation or fine-tuning step specifically for the complete workflow discovered in Stage 2. It ensures the prompts are perfectly tailored for how the agents actually interact and depend on each other within that specific best-found topology. It optimizes for those emergent interdependencies, making sure the whole system works together as cohesively and effectively as possible.
Got it. So stage 1, optimize the parts. Stage 2, find the best way to assemble the parts, guided by stage 1 insights. Stage 3, fine-tune the assembled whole, making sure the parts communicate and collaborate perfectly in that specific structure.
You got it. That's the three-stage process. Optimize parts, find assembly, fine-tune assembly.
That's a really clear, logical flow. But the million-dollar question, does it actually work? How did mass perform when they tested it?
Right, the results. The paper presents pretty extensive experiments across 8 diverse tasks to answer exactly that.
8 tasks. Okay, so they're testing for generality.
Yeah, they chose tasks covering a range of challenges. Complex reasoning like math and drop, multi-hop, long context understanding like hot putt QA, music, 2WikMM QA from long bench.
Those require piecing info together from lots of text.
Exactly. And also coding tasks, MBPP, human evil, and live code bench test output prediction. So really diverse set to make sure the framework isn't just tuned for one narrow thing.
What models did they use?
Primarily Gemini 1.5 Pro and Gemini 1.5 Flash, which are obviously very capable models. But they also did some key validation runs using Claude 3.5 Sonnet, showing it's not just tied to one model family. You can find all the details on tasks, blitz models, search spaces in tables 1, 2, and 4.
Okay, so what were the headline results? Did mass deliver?
Looking at the main results in table 1, yes, mass consistently yields really substantial gains over common, strong, multi-agent baselines.
Baselines
like standard implementations of self-consistency, self-refine, and multi-agent debate. These are popular methods. They involve scaling agents, but, and this is the key difference, they often don't explicitly optimize the prompts for how those agents specifically collaborate within that particular system.
Right. So mass isn't just putting agents in a debate structure. It's finding the best structure and optimizing the prompts for that specific debate.
That's the core idea, and the results seem to really back it up. Mass consistently and significantly outperforms those standard baselines across the board. It hits an average performance of 78.8% on Gemini 1.5 Pro, 74.3% on Gemini 1.5 Pro, flashed across those 8 tasks. Shows the approach works well on both models.
That's impressive average performance across such diverse tasks. How did it compare to other automatic design methods like ADS and AFlow?
Good question. They compare it against those two. ADS, which uses an LLM sort of meta agent to propose topologies, well, it often showed only subtle gains over simpler baselines in their experiments.
Why is that, do they think?
The paper suggests ADAS might get trapped proposing ever more complex topologies without adequately fixing the underlying prompts for the agents in those topologies. It's building complex architectures, maybe with under-optimized components.
Okay. What about AFlow?
AFlow uses Monte Carlo tree search for topology exploration. It was more competitive, doing well on some tasks like 2WikM QA and human eval. The paper thinks AFlow's relative strength there might come from its error log-based expansion phase, which gives some implicit feedback useful for guiding the process, maybe influencing prompts formatting indirectly, and it might have a more refined search space. But AFlow struggled significantly on other tasks like math and music, where mass still performed very well.
So the takeaway seems to be Mass's explicit stage optimization of both prompts and topology gives it the edge on average across the board.
That appears to be their key experimental finding, yeah. The consistent, significant improvements from Mass across this wide range of tasks really highlight how important it is to search and optimize in both the prompt and topology spaces, and do it in a coordinated, interleaved way, not just one or the other, and not just relying on implicit feedback.
Did they do ablation studies to show the impact of each stage?
They did, and those are really insightful. Figure 5 left and Table 5 show this. They start with a basic single chain of thought agent.
Okay, baseline.
Just adding APO, automatic prompt optimization, to that single agent gives a big initial jump. Then moving to stage 1 plus 1 PO, the block level optimization, that yields another large jump, about 11% average gain over the base.
Wow, okay, stage 1 is powerful.
Very. Then adding stage 2 plus 2 TO, the informed topology optimization, that adds another roughly 3% gain on average. And finally, stage 3 plus 3 PO, the workflow level prompt fine-tuning. That contributes another 2% gain.
That step-by-step breakdown is really compelling. It shows clearly that while that initial prompt optimization, even just at the block level, is hugely impactful, each subsequent stage, the informed topology search, the final system tuning, adds real, measurable value. It's the whole package.
Absolutely. And figure 5, right, drills down even more into stage 2, the topology search. It shows that both the good prompt optimization done beforehand in stage 1 and the smart pruning of the search space using those influence scores are critical. If you take away either of those, the gains from stage 2 shrink significantly. It really emphasizes how the stages build on each other.
Makes sense. Did they look at cost effectiveness at all? Is Mass efficient?
They did. Figure 6 shows optimization trajectories on the DRP task, plotting performance versus validation rounds, which is like optimization cost. Mass shows this nice, steady, gradual improvement. ADS and AFlow, in contrast, show more variance, less consistent upward trends. And they point out a potential practical advantage. Stage 1, block optimization, and Stage 2, topology search, could potentially be parallelized in Mass. You could optimize different blocks or search different topology regions at the same time. Iterative approaches like ADS and AFlow often have to wait for one round to finish before starting the next.
So maybe faster optimization time too.
Potentially, yeah.
Yeah.
And Figure 9 looks at inference cost on math. It plots accuracy versus tokens used, for example. Math sits favorably on that Pareto front, higher accuracy for a given token count compared to the standard multi-agent baselines like SE, reflect, debate.
So not just more accurate, but potentially more efficient to run once optimized too.
That's the claim, yeah. Better accuracy and better token effectiveness.
Okay, so Mass seems effective, efficient, and the staged approach makes sense. What did the actual best systems found by Mass look like? Did they learn anything general about what makes for a good Mass design?
Yeah, analyzing the discovered workflows was definitely insightful. Figure 7 shows an example trajectory for the math task, which is quite revealing. Well, math starts with a simple single COTI agent. In stage 1, maybe the block optimization finds that a multi-agent debate block with a specific optimized prompt performs well initially.
Okay.
But then in stage 2, the topology search, exploring combinations, might actually find that for math, simply aggregating outputs from multiple parallel predictor agents, maybe using self-consistency or voting, actually outperforms that debate block.
Interesting. So it looked good in isolation, wasn't necessarily best in composition for that task.
Exactly. And then stage 3 comes in and runs workflow-level prompt optimization, specifically on that best-found parallel aggregation topology, fine-tuning the prompts for that specific structure and aggregation method.
That's fascinating. It really drives home that there's no single best topology like debate or reflect that works everywhere. It's task-dependent, and optimizing the prompts for the winning topology is key. The search finds what works.
Precisely. It's the combination and the task's specificity. And based on findings like these, across all the tasks, they distilled 3 key design principles for building effective MAS with LLMs. These are summarized near the end of Section 5, and they're really practical takeaways.
Okay, what are they?
Principle 1, straight from Figure 2. Optimize individual agents properly before composing them. Get the building blocks right first. Don't try to compensate for weak individual agents by just adding complexity. Fix the pieces.
Makes sense. Foundational.
Second, build more effective MAS by composing influential topologies. Remember Figure 3 showing most don't help. Focus your search and design on arrangements that have shown positive influence, either through analysis like theirs or your own initial tests. Prune the space based on impact.
Be selective with structure. Got it.
And third, underscored by stage 3, model the interdependence between agents. Even with the right blocks and the right structure, fine-tune the prompts so they work together synergistically in that specific arrangement. Achieve this via workflow-level joint optimization.
Optimize parts, select influential structures, fine-tune the whole interaction.
That's the essence. And you can really see this reflected if you look at the example prompts they included in appendices D and E.
Oh, they show the actual prompts mass found.
Yeah, examples for different tasks and agent types. And they are not simple generic instructions. They're highly structured, very task-specific. Sometimes they incorporate things like data summaries or meta instructions that came out of the optimization process.
Can you give an example?
Sure. The debater prompt for Hotpot QA in Appendix E is a good way. It doesn't just say debate the answer. It instructs the agent to act as an expert fact-checker. Its core job is defined as meticulously reviewing proposed answers, identifying potential inaccuracies, explicitly requesting supporting evidence from the provided context, and challenging flawed reasoning.
Wow, that's a very specific, demanding role definition.
Exactly. And that level of specific, optimized prompting tailored for the agent's role within that particular debate topology found for Hotpot QA is clearly a huge part of why Mass works better than just using a generic debate setup. Mass finds these highly effective specific instructions.
Those principles provide such a clear roadmap. It really helps structure that chaotic knobs and levers problem we started with. This framework feels like a big step towards more rigor, more automation in MAS design, moving away from just guesswork.
I think so too.
Are there any limitations they mention? Areas for future work? No system's perfect, right?
No, absolutely. And they're good about discussing limitations in Appendix A. One point is, while their topology space covers many common effective designs chains, parallel, reflect, debate, it's not exhaustive.
Right. There could be other useful structures.
For sure. They mentioned maybe sparse communication topologies, where agents only talk when needed, is one area not fully explored here, but potentially interesting.
Who else?
They also mentioned that while their topology optimizer, the informed rejection sampling, is efficient for the space they defined, if you wanted to explore an even more complex or expanded design space in the future, you might want to incorporate more advanced search algorithms, like Bayesian optimization maybe, to improve sample efficiency.
Okay, potentially better search methods for bigger spaces.
And similarly, for the prompt optimization itself, they suggest its efficiency could potentially be enhanced. They plan to explore conditioning the APO process on textual feedback from error logs.
Ah, so instead of just knowing pass-fail, the optimizer gets told why it failed.
Exactly. Feedback like, Agent X hallucinated this, or Agent Y didn't follow the output format. That richer signal could potentially help the optimizer zero in on better prompts much faster.
Got it. So continuous improvement on search algorithms and feedback for prompt optimization seem like natural next steps.
Yeah, building on this really solid foundation they've laid.
Okay, so to wrap up this AI peer review, we've taken a really deep dive into an important paper that gives us a much more structured, principled, and potentially automated way to tackle the frankly daunting task of building effective multi-agent systems with LLMs.
Yeah, by analyzing that design space first, they really drove home two critical insights. The absolutely crucial role of getting the individual agent prompts right, that's often the biggest lever, and the surprising fact that beneficial topologies are actually quite rare. You need to be selective.
And their mass framework gives us a concrete three-stage playbook for automating this. Stage 1, optimize the individual building blocks first. Stage 2, use insights from Stage 1 to intelligently search for the best way to assemble them. And Stage 3, fine-tune the prompts for that specific system structure to nail the interactions.
And the results look really strong. Significant gains across diverse tasks, validating that optimizing both prompts and topologies in this kind of interleaved way is really key.
It definitely feels like a shift away from just manual trial and error, hoping things work out, towards a more principled, automated search process, guided by understanding what actually drives performance. Now, here's where it gets really interesting for you, the listener. Thinking about these three design principles, they pulled out optimize components first, compose influential structures, fine-tune the whole interaction. What does this mean for how you might approach designing your next multi-agent application? Are you spending enough time getting those individual agent prompts really solid before you start connecting them? Are you being deliberate, maybe even testing your topology choices? Or just adding steps like reflect or debate because they sound sophisticated?
It gives you a concrete blueprint, doesn't it? To move maybe from guessing towards more guided design.
Definitely something to think about as you build.